Okay, Bismillahirrahmanirrahim. Assalamualaikum, and let's continue on our next part of on synchronous generator control, which is particularly we're going to talk about on active power control. Okay, how do we control the active power? Basically, active power is a real power, which is also called a watt. Okay, unit watt. Okay, so first we need to find what is the relationship for active power control. We need to define what is the apparent power. The formula for apparent power is per phase. Okay, is V, the phase voltage, multiplied by the armature current conjugate. Okay, this is pretty much you guys should be very familiar with this equation here. And we know that this relationship between the generator voltage and the phase voltage, and this is formula ZS here. So you remember that ZS here, the synchronous impedance here, consists of two parameters, which is RA plus JXS, okay, which is armature resistance, and the synchronous reactance, okay. So ZS is combined, it's a combination of both armature resistance and synchronous reactance multiplied by the armature current, and we get a voltage drop across the synchronous impedance. So and then because of that, from this equation, then if you rearrange this equation here, so you bring the current to the other side, and you can get that the phasor current, the armature phasor current, is equal to the generator voltage minus the phase voltage divided by the synchronous impedances. Okay, and I just put this. This is just to show you in terms of magnitude and the voltage and the phase angle. Okay, so the generator voltage has a magnitude of E and the angle of delta. This is what we call the power angle. Okay, and minus the magnitude of the voltage, phase voltage, and the angle here is always set to be 0, because this we take this as a reference voltage and the voltage that we are going to fix. We always assume the voltage of the phase voltage always 0 degree. Okay, and then divided by the synchronous impedance at the angle of theta, and remember this theta here is the theta of the power factor. Okay, so and then if you just take the conjugate of the current, armature current, and what the conjugate does is basically you reverse the polarity of the angle here. Okay, so previously you have a positive angle for the generator voltage, and if you conjugate it, it becomes negative. For the phase voltage, it doesn't matter because the voltage is still 0 if you negative or positive it. And then the power factor angle for the synchronous impedance becomes negative theta. Okay, so that's just, so if you combine this IA phase, okay, all right, and you put it inside this formula here, and then you will have this equation here. So the per phase apparent power okay, is equals to P plus JQ, of course, and V phase multiplied by IA conjugate. And if you plug in IA into this equation, you will have this equation here. Okay, the V multiplied by, okay, this is a V phase here, okay, multiplied by the E minus this basically this is the equation for the I conjugate here. I just plug in here. Okay, sorry, this one here. Okay, and then after that we expand it. Okay, we expand the equation here. All right, so E multiplied by V divided by ZS, and then we have this cosine theta minus delta plus J sine theta minus delta, and then that is minus V squared divided by ZS synchronous impedance multiplied by cosine theta minus J sine theta. Okay, this is just mathematics. Okay, just expand the equation here in terms of cosine and sine. Okay, so after that, if you separate the real and imaginary part, so we can see that this expression here has the real and imaginary part. This is a real part, the imaginary part. We have a J constant there, and then if you separate them together, we can derive the equation for general expression for generated real power and reactive power as follows. Okay, so the real power, this is a per phase power. Okay, this is a per phase power. Okay, per phase power, per phase R. Okay, so equal to generator voltage minus the first phase voltage divided by synchronous impedance multiplied by cosine theta minus delta minus v squared divided by zs cosine theta. Okay, and for Q, the only difference is just basically you replace cosine to sine. Okay, it's cosine to sine. Okay, that's the only difference. It's the same formula except for the real power, it's a cosine on both sides, and for reactive power is sine on both sides. Okay. Okay, now let's take a look further. So from previous, we have this formula for the. Let's analyze only the active power for the time being. Okay, so this is the general equation for the active power control. All right. So analysis for the reactive power. Okay. So let's further simplify this equation, and we assume that the armature resistance is 0. So the synchronous impedance become JXS only. Okay, so we can further simplify instead of this two long equations. We can simplify for the per phase real power delivered by the generator. Okay, is equal to the multiplication of the two voltage, the generator voltage and the phase voltage, divided by the only synchronous reactance XS, multiplied by the sine of the sine of delta, sine of the power angle. Okay, so okay, this is just basically you do some manipulation of course you will see some cosine and cosine here, but basically when you simplify it, it becomes a sine of delta. All right. Okay, so basically there are some using some sine cosine formula to come up with this formula. Okay, so and then how about for Q? Okay, for the reactive power, for per phase reactive power, you can simplify that in terms of this one. Basically, it's equal to, okay, E times V divided by X multiplied by cosine delta minus V squared divided by synchronous reactance. And you can take these two parameters out and you can simplify it in this way. Okay, so finally your Q, the reactive power, relationship between the voltages and the reactance are, so the V divided by synchronous reactance multiplied by E cosine delta minus the magnitude of the V voltage here. Again, this is a phase voltage, this is the armature generator voltage, and this is a phase voltage. Okay. All right. So so the three phase power delivered. Okay. Now this is for only for per phase voltage. So how about three phase? It's not really that complicated. You just put a number 3. You must multiply the equation here by 3. Okay, so 3 times EV divided by XS multiplied by sine delta for the 3-phase real power. Okay, and for the reactive power is 3 multiplied by this expression here from previous year. Okay, all right. So that's it for the two formula. For how can we find the relationship between the real power and the voltages and the reactance and the power angle. Okay, so basically you can see that these are the three most important. So also for the reactive power will depend on the value of the phase voltage, the reactance, the induced voltage, and the power angle. So 3 parameters. Okay, so P, you can say that the value will depend on P and Q will depend on only these 3 parameters: the magnitude of the voltage, magnitude of the generator voltage, the phase voltage, and the power angle. So these are 3 most. If you want to take something out from this is it. Okay. All right. So if you plot, okay, let's take a look only for the real power. Okay, for the 3-phase power. If you plot that this graph here on the plane for this is power versus angle, okay, delta, you will have this kind of a huge a shape curve like a hill here. Okay, all right. This is because of a sine delta, a sine function. Okay, so you can see that there is a maximum. If you increase the angle, the power angle from 0 to a certain value, okay, we increase this way, we will increase the real power, okay, supplied by the generator. But there is basically a maximum power until to a certain value, okay. At the angle of 90 degrees, okay, you can see that the power will be maximum at this point. Okay, and if you maximum between sin delta at 90, sin delta at 90 means 1, right? Okay, so the maximum value will just be 3 multiplied by the generator voltage multiplied by phase voltage divided by the synchronous reactance. Okay, so that is the formula if you want to find the maximum voltage. Okay, so what does it mean? So basically this graph here, okay, as I said before, is a curve. This is, okay, I forgot to mention, this is what you call a power angle characteristic curve. Okay, I can say this is a real power lah. Okay, so it is basically a curve to describe the relationship between the real power and versus the power angle delta. All right, so as you can see, it's a curve. It's like a half of sine wave. Okay, so if we increase the power and then the angle between the induced voltage and terminal voltage will also increase. Okay, what is delta? Delta, remember, delta is basically the angle between the V and E. Okay, so that is delta, right? So this is what function here. So if we change, if you increase the power, let's say the generator will supply, let's say the customer, the load require 100 megawatt. Then the generator will need to supply 100 megawatt. Okay, so but there is a certain value here. Okay, but in order to supply a certain value of power, there must be a certain value of delta. Okay, power angle, and then the delta can operate only a certain region because, okay, as I said just now, okay, so it will increase as the power increase. This is what the second bullet tells you lah. Okay, so in other words, when V and E are constant, okay, if you have, let's say, you want to maintain the V and E, okay, for example, then by varying the prime mover input to the generator, the prime mover, what is a prime mover? Prime mover is like, for example, for the hydro generator and the steam turbine or gas turbine. Okay, the power angle is changed. Yeah? And then if you change the power angle, then the real power delivered by the generator will also change. Okay, so basically, if the generator receive a new power angle, a new power requirement, then it will change this power angle in order to increase or decrease the real power delivered by the generator. Okay, so it depends. Sometimes generator can go up this power and can go between this angle to this angle. Okay, so typically the generator will operate below this maximum value lah. Okay, so okay, what I didn't mention yet, what is actually this point here? Okay, this point here we call a maximum power is basically what we call it as a static stability limit. Okay, so stability basically is not covered in this topic. Actually, it's a very large topic to explain you, but just accept for the time being that at angle delta equals to 90 degrees, you basically, when you have this situation, okay, when the angle of V and the angle of E is exactly or very close to 90 degree, the generator will experience what you call a static stability limit. What does that mean? That if the angle go beyond the 90 degrees, the generator will produce a very, very large current and mechanical forces, and the generator will steps out of synchronism, meaning that the generator will be no more synchronized to the network. Okay, so that actually require a whole lot of new explanation, but just accept for the time being that for the generator to operate safely without any issues of stepping out of synchronism, you will need to operate within this region here, Okay, normally it will not go beyond very close to P, to the maximum, to the angle. Okay, so typically the generator operates between 15 to perhaps 20 degrees of angle of delta, because you're going to be a very only safe side region here. They want to go to the end high side of the power angle. Okay. All right. Now let's go back to reactive power control. Okay, we've talked about that. For active power control, the formula is this one is 3 multiplied by EV divided by S multiplied by sine delta. Okay, so how about the Q, the reactive power? Okay, so from previous we know this formula, right? So I've shown you that the three-phase Q reactive power is equal to 3 multiplied by V divided by XS multiplied by E cosine theta minus V. Okay, that is for the reactive power control, reactive power formula, sorry. So typically for a very small delta, let's say delta perhaps around maybe 10 degrees or 12 degrees, kan? So you can see that cosine of delta is very, very close to 1. It's very, maybe 0.8 or 0.9, something like that. Okay, so we can approximate that cosine of theta is equal to 1. Okay, for a very small angle of degree of delta lah. Because this is what typically generator will operate. It will not operate at higher like 70 degrees or 80 degrees. No. Okay, so it will because you know that cosine of 0 is 1, right? So cosine of a very small number is very close to 1. Okay, so if we assume that cosine of delta equals to 1, then we can approximate that the reactive power, okay, Q, delivered by the generator, okay, delivered or absorbed, depends. Q can flow either into the generator or out from generator. Okay, so the formula will be 3 multiplied by V, the voltage phase divided by synchronous reactance, multiplied by the the difference of the magnitude between the generator voltage and the phase voltage. All right. So do you guys remember? Okay, previously from our last lecture that when the generator voltage is greater than the phase voltage, you will have this value Q here, Q3 phase here, will be greater than 0, right? So because this is positive, E minus V is positive because E is greater than V. This is always positive number. This is always positive number. Just as 3. Okay. So and then what does it mean that if you have Q greater than 0, remember from the power triangle. Okay, for the power triangle, this is S, this is P, this is Q, right? Okay. Okay. If Q greater than 0, then you will basically the generator, the system operate at a lagging power system. Okay, and lagging power system meaning that the Q will be supplied by the generator, will deliver the reactive power. Okay, instead of absorbing, will deliver, and the generator is said to be operated at overexcited system. Okay, or maybe call it overexcitation. All right. So vice versa. On the other hand, if you have the voltage E here less than V, okay, meaning that this expression here will become less than 0, and of course Q, the three-phase power will be less than 0. So that means that the generator absorb reactive power. So it's in this region, Q less than 0. All right. So we'll absorb reactive power from the system, meaning that the generator is experiencing a leading kind of load, and the excitation system is what they call under-excited. Okay. So in reality, typically generator operated in over-excitation mode. Very rarely that the Q is less than 0. We are talking about real situation. Okay. So mostly load, because majority of the load are inductive. As you can see outside there are big motors, and aircon are also using electric motors. Okay. So electric motors normally are all inductive loads. Okay. So in conclusion, the flow of reactive power is governed by the difference in the excitation voltage E and the voltage at the bus V. Okay, so so it doesn't really much have a difference in terms of angle delta, but it's basically majority. I mean, the big portion of the Q is governed by the difference of the angle phase and between the magnitude between generator voltage and phase voltage. Okay. So, and then just a few note that the adjustment of excitation voltage E is achieved by the generator excitation system. What is the generator excitation system? Is basically where you control the field current, and then you will control the flux, and the flux will control the generator voltage. Okay, so this whole system is what we call the excitation system. Okay, so remember there's a circuit here where you have a field current and a resistor, and you have another adjustable resistor, right? Okay, and there's a field current flowing here, and then this current will generate a voltage here. It is induce this E voltage. Okay, that is it. This system here is basically the excitation system. Okay, all right. So okay, I'm going to show you maybe okay, we continue on our next video where we're going to discuss on a few example on how to analyze the theory or the topic that we just explained just now. Okay, so we'll continue on our next and last video for this week. Okay, I'll see you again.